All right, here we go with a question about diffraction gratings. This is HL, not SL. If you are an SL student, skip this one, and let's go for it. All right, now if I had a klaxon for classic question, I would be sort of blaring it out right now. This is one of the very common questions. I've seen this come up recently in paper 1 and paper 2, so it's really a good one to be well versed with. We've got light of wavelength 5 times 10 to the minus 7 meters, incident on a diffraction grating which has 400,000 lines per meter. That's something we're going to have to think about, and we want to know how many maxima can be observed with this diffraction grating. Now again, as I've said previously, there are ways of ruling out answers here. We're just going to go brute force right through to the answer, and then we'll talk about strategies at the end. We're going to use our equation n lambda equal to d sine theta, and we're going to try and calculate the maximum n that we can see. This is going to require us to know d, lambda, and sine theta max. Now, as with any time you do this kind of question, first things first, we're going to make sure that we know what d is. Now, in this case, we're told that there are 400,000 lines in every meter, and so therefore, what we're going to have to do to find out the d, which is the separation, I should have an m here, between those slits, is just going to be 1 over that. It's going to be 2.5 times 10 to the minus 6. We also need to think about theta. The maximum theta for diffraction is going to be 90 degrees, because anything beyond that is somehow going back on ourselves, and that doesn't happen. So we're going to put in theta equal to 90, sine theta maximum is equal to 1. And using those two numbers, we're then going to think about what we can observe. So we'll calculate n max. That's going to be 2.5 times 10 to the 6. We're going to have times 1, which are sine theta, and we're going to divide by 5.8 times 10 to the minus 7. Now, this is where you have a little job to do. Firstly, there's a few little steps here. Firstly, we've got 4.3. Now, fortunately, this is a number close to the whole number. All right, but what we have to do in this case is always round down. Reason being is that we can only observe the order before that number, and n is an integer. So if we get an answer which is 4.3, well, we can see 1, 2, 3, and 4. We cannot see 5 because 5 has not been achieved. Even if we got 4.8 here, we do not round up because we've not surpassed that value of 5. So we have to round down to the nearest integer. So very common answer here would be 4, but we've forgotten about the fact that actually we have more maxima to see. For every 4 on the top of our diffraction pattern, we're going to see another 4 on the bottom. So actually we're going to see 8. Again, you might think just double it, but actually we've got the one in the center as well. So actually when we're working out the number of maxima that we can see, we're going to take 2 times n max, we're going to add 1, and we're going to take 2 times 4 plus 1 is equal to 9. Okay, so actually we're accounting for the 4 maxima on one side of the principal maximum, 4 on the other side, and the principal maximum itself. So we've got 4 plus 1 gives me 9. Now again, strategies. If we're thinking about this kind of question, you notice that we've got 2 times 2n plus 1. Well, that is always going to give you an odd number. So it means that 4 and 8 are immediately ruled out. And if you think about that, actually 4 and 8 could have been two of the more obvious answers to get here. 4, because that's what we get from our maxima and from our calculation, and 8, because that's double, but we've forgotten the central one. Adding 1 makes 9. So quite cheeky, sort of tricky question here. Definitely a common one that I've seen many times before. Make sure you know how to do this one, folks.